Hi, in this video, we're going to learn how to calculate value at risk for a Pearson distribution in Microsoft Excel. Let's begin by reminding ourselves what is value at risk. Imagine we have some data on returns, such as returns on an investment, and we represent the data in a bar chart like this. For example, this bar shows 5% returns happen about 25% of the time. And this bar shows 20% returns happen about 5% of the time. And all these bars add up to 100%. We could also fit a distribution to the data, and the area under the distribution would be 100%. Now imagine we split the area into two, 95% on the right and 5% on the left. Then value at risk, or VAR for short, is the return that separates the two areas. In this case, VAR is the worst possible return that happens 95% of the time. I'll repeat, VAR is the worst possible return that happens 95% of the time. The 95% is called the confidence level. It doesn't have to be 95%. It could be 90% or 99% or some other percent. Regardless, VAR would simply be the return that separates the two areas. Sometimes people use VAR in the context of losses instead of returns. In that case, the distribution would flip horizontally and VAR would be in the right tail. This is something to keep in mind when we look at the custom function later. Now, if the distribution is nice and simple like a normal distribution, we can calculate VAR using any method that returns the percentile of a normal distribution. In Excel, we can use a native function called norm.inv. But in practice, the distribution is unlikely to be as nice and simple as a normal distribution. It's likely to be asymmetric, and it's likely to have fat tails. The asymmetry is measured by something called skewness, and the fatness of the tails is measured by something called kurtosis. Skewness and kurtosis. The normal distribution has a skewness of 0 and a kurtosis of 3. So how do we calculate VAR for a distribution whose skewness is not 0 and whose kurtosis is not 3? There's a family of distributions called Pearson distributions, which can fit all possible combinations of skewness and kurtosis. This is what they look like compared to the normal distribution. There are 5 types of Pearson distributions. Type 1 is related to the beta distribution. Type 3 is related to the gamma distribution. Type 5 and type 6 look somewhat similar. They are related to the inverse gamma and inverse beta distributions respectively. Type 4 is special. It is not related to any known distribution. In fact, it has a reputation for being difficult to implement in practice. I think one of the reasons why the Pearson distributions aren't used more widely is because type 4 isn't easily accessible to end users. But as we will see later, we can easily access type 4 in Excel using QRS Toolbox. These 5 types of Pearson distributions cover all possible combinations of skewness and kurtosis. But how do we calculate VAR for a Pearson distribution? More specifically, how do we calculate VAR for a Pearson distribution in Excel? Simple. We use a custom function called qrs.var.pearson. It accepts 6 parameters. The first parameter is the confidence level, followed by the mean, variance, skewness, and kurtosis. The final parameter is an optional parameter called tail. It determines whether to calculate VAR in the left tail or right tail, as mentioned earlier in this video. Now, let's see it in action. The first thing to do, if we haven't already done so, is to add QRS toolbox to Excel. To do that, click Insert on the Excel ribbon, click Get Add-ins, search for QRS toolbox, click Add next to the correct search result, click Continue after reading the terms and privacy policy. Then we need to start our free trial of qrs.var.pearson. To do that, click Show Task Pane, click Sign in with Microsoft, click Custom Functions, click qrs.var.pearson, read the documentation, and click Start my 7-day free trial. And we're ready. Right, now let's explore this workbook. Cell B1 contains the confidence level, which we've set to 99% for now. Cell B2 contains the mean, which we've calculated using the data in cells B10 to B2197. The data here actually represents daily percentage changes in the price of Bitcoin from 2015 to 2020. So they're actually daily historical returns on Bitcoin. And we've calculated that mean using Excel's built-in average function. Similarly, for variance, we've used historical data and Excel's built-in var.s function. And for skewness, we've used skew. And for kurtosis, we've used kurt. These functions are all built into Excel. In practice, we might not use historical data at all. For the mean, we might use analyst forecasts or some other forward-looking estimate. For variance, skewness, and kurtosis, we might use simulated data or even proxy data. For example, if we were to calculate VAR for a relatively new cryptocurrency, we might use data on Bitcoin as a proxy, since Bitcoin has been around much longer. Cell B6 contains the VAR calculated empirically using the percentile function. We've included here purely as reference. Now let's calculate VAR for a Pearson distribution. Before we do that, let's find out what type of Pearson distribution it's going to be. To do that, we can use the free qrs.pearson.type function, which takes the 4 moments and returns the type as a Roman numeral. In this case, it's type 4. And if you recall, I said type 4 has a reputation for being difficult to implement. And yet, with QRS Toolbox, we now have type 4 at our fingertips. So let's go on and calculate VAR for a Pearson type 4 distribution. To do that, we use qrs.var.pearson, give it the confidence level, the mean, variance, skewness, and kurtosis. We'll skip the tail parameter for now. And within 2 seconds, or less than that, we've calculated VAR for a Pearson distribution, and a Pearson type 4 distribution at that. The result is negative 10.16%, which means to say in 99 out of 100 days, the worst possible return on Bitcoin is negative 10.16%. Okay, so in 99 out of 100 days, the worst possible return on Bitcoin is negative 10.16%. So that's what this VAR is trying to say. We can change the confidence level to say 95% to see what happens. We get negative 5.88%, again pretty close to the empirical VAR. How about a confidence level that's closer to 1, 99.9% say? We get negative 18.21%, again very close to the empirical. Let's go even further, 99.99%. We're in the extreme left tail now, and yet it took less than 2 seconds to calculate a VAR of negative 30.24%. Again, very close to the empirical VAR. We could assume that we have losses instead of returns and flip the tail. So we set the tail parameter to 1 to evaluate the right tail instead. And this time we'll get a var of 26.95%. It's positive because we're now in the right tail instead of the left. Okay, and that's assuming we have losses instead of returns. But since we really do have returns, let's reset it to the left tail by putting -1. Okay. What happens if we use a normal distribution instead? Well, remember the normal distribution has a skewness of 0 and a kurtosis of 3. So let's do that. And we get a var of -14.1%, which severely underestimates the empirical var, as well as the one given by the Pearson distribution earlier. And that's it. Now, if you find QRS var.pearson useful and would like to use it beyond your free trial period, you may purchase the right to use it indefinitely with a one-time payment of only $99 US. And that's it. Thank you for watching this video.